Welcome friends, Igor is here, and in this video we will study properties of the dimension of vector spaces. In this lesson we will learn that linearly independent sets cannot be too large and spanning sets cannot be too small. Also, we will discover how the dimension of a subspace of a vector space relates to the dimension of the ambient vector space. Let's get started. Given a set of vectors in a vector space, we are often interested to know whether this set is linearly independent and if this set spans the vector space. In general, these are two independent questions which are not related to each other. However, as we will see today, one of these properties can automatically follow from another if you add the dimension considerations into the picture. Our first result shows one possible way to extend some linearly independent sets to larger linearly independent sets. Suppose S is a set of linearly independent vectors in a vector space V, and let's assume that we can find a vector W which does not belong to the span of S. Then, if we extend the set S by adding this vector W, then the extended set is still linearly independent. Let's denote the vectors in the original set S as v1, v2, vm. We are assuming that these vectors are linearly independent. And let's look at the extended set S tilde, which includes the vectors v1, v2 through vm and the vector W. To prove that the extended set is linearly independent, we construct a relation of linear dependence on this set. If the scalar that comes with the vector W in this linear combination is a non-zero scalar, then we can use properties of vector spaces to solve this equation for the vector W. But this is an expression of the vector W as a linear combination of the vectors in the set S, which contradicts our assumption that the vector W does not belong to the span of S. The assumption that alpha m plus 1 is not equal to 0 led to a contradiction, therefore this scalar must be equal to 0, and the relation of linear dependence simplifies to the following one. Remember, in any vector space, if you scale a vector by the zero scalar, you get the zero vector. But now this is a relation of linear dependence on the original set S, and we assumed that this set is linearly independent. This means all scalars in this relation, alpha 1, alpha 2, up to alpha m, must be equal to 0. But if you look at what we achieved, we have shown that all scalars in the original relation of linear dependence on the extended set S tilde must be equal to 0. Therefore, the only relation of linear dependence on the set S tilde is the trivial one. This means this set is linearly independent. This is exactly what we are going to prove. Now, we are going to draw an analogy between the vector spaces and the Goldilocks story. In vector spaces, some sets are too big, they are linearly dependent. Some sets are too small, they do not span the vector space, and some sets are just right, they are the basis of the vector space. Suppose we have a vector space V which has dimension t. Also, we take a set S of vectors in this vector space which contains m vectors. Then, if m is greater than t, then S must be a linearly dependent set. If m is less than t, then S cannot possibly span the vector space. If m is equal to t and S is linearly dependent, then S automatically spans V. Also, if m is equal to t and S spans V, then S is automatically linearly independent. Before I prove this result, let me explain how it is useful. Suppose you're given a set of vectors in the vector space and you need to decide if this set forms a basis of the vector space. The first thing you do is count the number of vectors in that basis. If the number of vectors does not match the dimension of the vector space, you know right away it cannot possibly be a basis. However, this result shows that if the size of that set is just right, it's enough to check only one property. For example, if you show that the set is linearly independent, then it will automatically span the vector space, and therefore it will automatically be a basis for that vector space. I'm going to take a basis B of the vector space V, and because we assumed that the dimension of the vector space is equal to T, B is a linearly independent spanning set for V which contains exactly T vectors. To prove the first claim, let's observe that in the vector space V we have a spanning set B of size T, and we proved in a previous video that every set with more vectors than the size of a spanning set must automatically be linearly dependent. Because S contains more vectors than the set B, it means S must be linearly dependent. I will prove the second claim by contradiction. Let's assume, on the contrary, that S does span the vector space V. The set B as a basis of V is in particular a linearly independent set. What it means is we have a linearly independent set of size T which is larger than M, the size of a spanning set S. This is impossible, this is a contradiction, therefore S cannot span V. To prove the claim 3, let's again use proof by contradiction. We are going to assume the opposite of our desired conclusion. Namely, we are going to assume that the set S does not span the vector space V. Then we can find the vector W in the vector space V, which does not belong to the span of S. By the result we proved earlier in this video, if we enlarge the set S by adding this vector W, then the larger set S tilde is still linearly independent. The original set S contained M vectors, therefore the enlarged set contains M plus 1 vectors. We assumed that M is equal to T, therefore the set S tilde contains T plus 1 vectors. Also, we have the set B, the basis of the vector space, which spans the vector space V and it contains T vectors. But this leads to a contradiction, because we have the set S tilde which contains T plus 1 vectors and it is linearly independent. It is a larger set than the spanning set B of T vectors. We know this is impossible, therefore our assumption was wrong, and the conclusion is that the set S must span the vector space V. Yet another proof by contradiction to prove claim number 4. We are going to assume the opposite of our desired conclusion. We are going to assume that the set S is linearly dependent. This means that one of the vectors in this set can be expressed as a linear combination of the other vectors in this set. Let's construct a new set S tilde by deleting this vector which is expressible as a linear combination of the other vectors in S. We have discussed in one of the previous videos that doing so does not change the span of the set. So if S was a spanning set for V, then this new set S tilde is also a spanning set for the vector space V. But this spanning set contains one fewer vector than the original set S. The set S contained M vectors. We assumed that M is equal to T, therefore it also contains T vectors. This means the set S tilde contains T minus 1 vectors. But at the same time, we have the basis, set B, which is linearly independent and it contains T vectors. So, a linearly independent set B is a larger set than a spanning set S tilde. We know this is impossible. This is a contradiction. Our contradiction was caused when we assumed that the set S is linearly dependent. Therefore, the conclusion that we draw from this is that the set S must be linearly independent. In one of the previous videos, I boasted my ability to just glance at a set of vectors and say that it does not span the vector space. But now you see that there is no magic in this ability. For example, given this set of 3 vectors in the vector space of 2 by 2 matrices, we know right away this set cannot span the vector space because the dimension of the space is 4 and this set contains only 3 vectors. This set is too small to be a spanning set. Any spanning set in a vector space of dimension 4 must contain at least 4 vectors. However, please be careful in drawing conclusions about the linear independence properties of this set. This set of 3 vectors can be linearly independent because it does not contain more vectors than the dimension of the vector space. However, just because this set is smaller than the dimension of the vector space does not automatically make it linearly independent. Now, let's see how the dimension of a subspace of a vector space relates to the dimension of the vector space. And the first result is this. Suppose we have a subspace U of a vector space V, and U is a proper subset of V. Then the dimension of U as a vector space is strictly less than the dimension of V. Let's say that the dimension of U is M and the dimension of V is T. We want to prove that M is strictly less than T. If U has dimension M, it means there is a basis B of U which has size M. However, this set of vectors B in U is also a set of vectors in V, because every vector of U is a vector in the vector space V. If M were greater than T, then B would be a set of vectors in the vector space V of dimension T of larger size. It would force this set B to be linearly dependent in V. However, B is a basis for U, therefore it is a linearly independent set. This is a contradiction which shows that M cannot be greater than T. If M were equal to T, then B is a linearly independent set of vectors in the vector space V which has the right size. By the Goldilocks theorem, it would mean that B is automatically a spanning set for the vector space V. But B is also a spanning set for the vector space U because it is a basis of U. This means that both U and V are equal to the span of B, therefore they are equal as sets. This contradicts our assumption that U is a proper subspace of V. This contradiction means that M cannot be equal to T. So what's left? The only option that's left is that M is less than T, and this is exactly what we were trying to prove. Next, let's prove that if the dimension of a subspace of the vector space is equal to the dimension of the ambient vector space, then in fact they are equal as vector spaces. This is going to be proof by contradiction, so let's assume that U is not equal to V. Then U as a subspace of V is a subset of V, and we assumed they are not equal as sets. This means U is a proper subset of V, and by what we just proved, as a proper subspace of V, U must have the dimension that is strictly less than that of V. This contradicts our assumption that U and V have the same dimension, and therefore we are forced to conclude that U is equal to V. Now, if you put the last two results together, this is what we get. If we have a subspace U of a finite dimensional vector space V, then the dimension of a subspace does not exceed the dimension of the ambient vector space. Moreover, the equality is possible if and only if U is the same as V. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will look at the rank and nullity of matrices. I will see you later.